Okay. Hello, everyone. My name is Brandon Reagen. I'm on the faculty here at NYU. I'm in the ECE department within the Tandon School of Engineering. I am also the lead PI on the Cryptolets program, which is why you're all here. And so in today's webinar series, I'm going to overview that program, what it is, what we're trying to accomplish, who the members are, and ways that you can get involved. And then beyond that, I'm also going to go into some of the initial work that's already been done by folks here at NYU in developing some of the first hardware implementations of cryptographic IP that have been open source today. So this is going to be for point addition. So if you're not familiar with what point addition is, it's a common computation used within zero knowledge proofs. So, and just to be clear, this is actually the second lecture in the Cryptolets speaker series. Ramesh was really generous and agreed to go first. I couldn't make it. So if you are following along linearly, it probably makes sense to watch this one first because it is a overview of the program. But they're all recorded, so you can do whatever you want. So Cryptolets is a program for accelerating cryptographic computing. And what do I mean by that? Cryptographic computing to me is a set of new and exciting technologies based on cryptography that are going to allow us to do things that we otherwise couldn't do today. So think about data we share or what we're actually able to compute. With cryptographic computing, we're getting new capabilities. Now, there's a bunch of different flavors of this technology, but the two ones that I think most about and I think are really exciting to think about are homomorphic encryption and zero knowledge proofs. So if you haven't seen this before, we'll just review them quickly. In homomorphic encryption, it starts off just like regular encryption, where you take your data, you encrypt it, and you send it out to the cloud. But where in traditional encryption, you only get protections over the network. As soon as you get to the cloud, right, you have to decrypt it to do your actual computation. With homomorphic encryption, the way that the data is encrypted leaves the underlying data malleable. That means that any computation that you apply to the encrypted ciphertext automatically applies to the underlying plaintext as well. So with homomorphic encryption, you can encrypt your data, protect it over the network, and keep it encrypted in the cloud, apply your computations from your cloud computing workload, return the encrypted result to the client, you get the exact same result from the computation, and you get the ultimate form of sort of confidential computing or privacy preserving computation. Another technique or technology is called zero knowledge proofs. You might have heard of this one before. This allows you to prove something is true, that you know something, that you have something, or that you know how to accomplish something without revealing anything about the actual data or information, right? So you preserve the privacy of whatever you know, but you can prove to someone else that you know it. This one's a little more abstract. It's kind of easier to understand with an example. So the one that I typically like to give is imagine you're Alice and you want to go see a movie, and Bob, is a ticket salesperson. So Alice wants to see some age-restricted movie. Bob says, "Okay, show me your ID," right, to do age verification. But this is kind of it doesn't really make sense if we take a step back and look at this, right? All Alice wants to do is go see a movie. She doesn't know Bob, and she has to give Bob her driver's license to prove her age. Well, your driver's license has your eye color, your height, your date of birth, your picture, and it even has your address where you live. That's a lot of information to give up just to see a movie. So instead of this sort of um, old way of doing things, if you had zero knowledge proofs, what you could do is you could inspect the ID, you could run a zero knowledge proof computation on the ID, generate a proof that I am Alice, I am over whatever, 17, and I'm able to see this movie, and give that to Bob. Bob could check it and verify that you are old enough, let you in, and that proof doesn't actually reveal any of that personal private information about Alice. So potentially very powerful. All of these technologies, super exciting, but we don't really use them today. We do, but not as much as we would like to. And the reason is that they're way too slow. And when I say too slow, I mean they're like 4 to 5, it depends how you count, but 4 to 5 orders of magnitude slower than their plain text alternatives. This is way too slow for most applications today. So what are we thinking about doing? We're thinking about building custom hardware accelerators to bridge this performance gap. But the challenge is that the average accelerator today is going to get me like 2 to 3 orders of magnitude speed up. And again, I want 4 to 5. Now, I want to get into the Cryptolets project by saying there's been tons of amazing work by all of us in academia and in industry and getting there. But to really get this 4 to 5 orders of magnitude speed up and go from a standard 3 orders of magnitude improvement to 4 to 5, it looks like it's going to need a communal community effort. So maybe it's time for all of us to start working together, use shared infrastructure, putting all of our ideas in one standard place to bridge the remaining gap. And that's the foundational motivating idea for the Cryptolets program. So Cryptolets is a CERC grant. So what that means is that it's actually an infrastructure and community development grant support. It's not actually for fundamental research. It's to build up tools, infrastructure, and community supported by the NSF. And what we're tasked with doing is building up all of this open source hardware infrastructure and the community around it to accelerate cryptographic computing and making it practical for today's use cases. And so if we look at what the challenge is with doing cryptographic research today, there's quite a few. The first challenge is that everything's fragmented, right? We have cryptography, we have computer architecture, we have EDA and CAD, we have verification, benchmarking, and testing. All of these things, everyone has their own way of doing it, everyone has their favorite way of doing it, and everyone has a lot of sort of siloed expertise, right? Within cryptography, we have all these different protocols for zero knowledge proofs. We have multiple different protocols or methods for homomorphic encryption as well. It would be nice if we had a standard way of talking about them. Within computer architecture, everyone has their favorite accelerator. We have vectors, we have systolic arrays, we have VLIW style. But again, they're all housed within their own universities and institutions. Same thing with CAD and verification flows. And now to make this slightly even more complicated, it tends to be distributed around the globe, right? So we have amazing researchers from all over working on the same problem, but we don't quite have that standard way of communicating with each other's yet. So we lack standard shared hardware IP, common benchmarks, and robust verification flows. This is all the challenges that Cryptolets are trying to solve. So the ideal result from our project will be we'll have this Cryptolets IP library. So you'll be able to go on to GitHub, just access a bunch of hardware IP cores, EDA flows, verification flows, and I'll talk more about what else we're going to be offering through it. You can take exactly what you need, or if you have your own core, you're totally welcome to commit it into the Cryptolets repo and share it with the world so others can build on what you've done. So you have this IP repository. You can pick and choose all the different IPs you want, assemble them into your protocol accelerator, something say for fully homomorphic encryption. Then you can use our EDA flows to build hard IP blocks. You can use our verification flows, our validation flows, our benchmarks to understand the performance and correctness guarantees and have something that's hardened and fabrication ready that you actually trust and that you can share potentially with the community. So our goals are to create common grounds for collaboration through this IP repository. And as researchers, to bridge this final sort of order of magnitude performance gap that still remains from cryptographic computing and to lower the barrier of entry. I suspect that many of you on the call may already be in the cryptographic computing community. And hopefully you remember what it was like to get started here, perhaps reading your first fully homomorphic encryption or zero knowledge proof paper. It's not an easy lift. So we're hoping that with Cryptolets, with all these webinars, speaker series, with the workshops, tutorials we do, we're just going to make that much, much easier. And so let me now introduce the team. So we have a really amazing team of experts here. I'm the lead PI. I'm Brandon. I'm from New York University. The other lead, the project manager, is Warren Savage. He's also on the call. He's excellent from Rock Savage. Also from NYU, we have Siddharth Garg, EDA expert. Austin Ravinsky, also EDA expert and a CAD VLSI expert as well. And Ramesh Kari, who's done all sorts of EDA, CAD, chips, automation flows, machine learning as well. From CUNY, we have our crypto experts, Rosario Gennaro and Tushar Joyce. They're going to be helping advise us to make sure we're doing the right things cryptographically. We're looking at the most interesting protocols and we're not missing anything. And Tushar in particular has an expertise in benchmarking, so he's going to be focusing on the performance benchmarking efforts. We've also partnered with Stanford, so we have Cherry Tombe, who is a VLSI chip design expert. He's going to be helping with a lot of the chiplet IP that I'll talk about in a future slide. And Caroline Triple, who's our formal verification expert and is already working on bringing up formal verification flows for Cryptolets. So within Cryptolets, we like to think that there's three pillars that we're going to be offering. The first is obviously our IP library. That's the one that I've talked the most about. We're going to open source hardware IP for hopefully everything that you would need to accelerate cryptographic computing. That's going to include RTL tests and reference implementations. We hope you can get active and join us there. Pillar 2 is all about interconnecting chips and EDA. So you may be asking, okay, the name Cryptolets, I understand where crypto is coming from. Where's the lets coming from? That's coming from chiplets. So we want to be able to scale out our accelerators to multiple chips. And to do that, we need chiplet IP. So we are working on developing open source chiplet IP that will be open and available to everyone participating in the Cryptolets program. And we want standard, robust EDA flows. So even if you're not a chip EDA expert, you'll be able to run things down and have them fabrication ready. And then, of course, in pillar 3, that's all about evaluation. And there's two things we're going to focus on. The first is validation and verification. As I said, Caroline's going to help us with the formal verification flows that's already underway. So we're going to be testing for both correctness and for side channels to make sure that all of these things don't leak any information. We're also going to be doing performance benchmarking, and that's going to be led by Tushar Joyce. And I suspect many of you are here because you are already in the Google groups, but in case you're not, please sign up. So if you send an email to this address, you'll be in our mailing list, you'll be in our Google group, and you'll be informed of all of our releases and upcoming events. So please join that. So in pillar 1, this is our crypto IP library. Within that, we like to think that there's 3 levels. There's a foundational level, a kernel level, and a protocol level. So what we did is the foundational level is composed of foundational models, and these are sort of the standard things you always see in cryptography. So modular multiplication, modular addition, field inversion, point addition, which we'll talk about later. And if you've done garbled circuits, things like half gates, AES, and stuff like that. And the way that we came up with these, we surveyed the major forms of cryptographic computing, fully homomorphic encryption, zero-knowledge proofs, and secure multi-party computation, and several instances of that within there, and looked at what was being used and tried to make sure that we had everything covered. And then building on this sort of foundation model, we can use those foundation IPs to build more interesting kernels. So these are things like number theoretic transform, basis conversion, Hadamard multiplication, multiscalar multiplication, sum check, oblivious transfer, all the sort of standard functions that you typically see in cryptographic computing. We drew up this table quite locally within the team. If you're a member of the Cryptolets community and you think we missed something, please let us know. We'll add it to our roadmap and make sure that we include it in the repo. Then what we're going to do is we're going to use the foundation and kernel modules to build full protocol accelerators. So these are 2 examples from my lab. The Osiris systolic FHE accelerator, which was recently published at TACO this year, and ZK Fire, which is our ZKP accelerator, also published earlier this year at HPCA. And so you can see how these accelerators just compose a bunch of the different units, the basis conversion. That's going to be right here. Number theoretic transform, Hadamard multiplication. So we're going to take those kernel accelerators and use them to instantiate full exemplar protocol accelerators to do the actual computations of fully homomorphic and zero-knowledge proofs. We're very excited about that. So in the second pillar, this is all about chiplets, EDA, and system scaling. So monolithic chips are great. A lot of the work we're still seeing in cryptographic computing is considering monolithic chips, potentially very large ones. But eventually you hit the reticle limit. So the maximum amount of performance you can get per reticle area is going to be limited. We need more. You can also potentially run into yield issues when you have these massive chips. So we want to look at having more smaller chips and distributing the computation across them. To do that, we need chiplet systems. And so with Cryptolets, what we're looking to do is actually release chiplet IP, as I mentioned earlier. The thought is that this is going to be UCIe style. So you will have direct, you can see it here, die-to-die interfaces to talk between chiplets. That's all going to be open sourced and part of the Cryptolets project. We're currently thinking to target ASAP 7 and Global Foundries 12 nanometer. That's to give everyone, so anyone can participate with ASAP 7, fully open source, anyone can do it. And with Global Foundries 12, that means if you do actually want to prototype a chip, you will have a route to that. Now, in addition to just the IP, we're also planning to release standard chiplets that folks are just going to use over and over and over again in these system in package designs. So first, we're planning to release a hub chiplet. You can see that one here. This is just your standard sort of controller interface chiplet where it just has a bunch of CPUs, so you can control the system, tell it what to do, and orchestrate all your work and data movement across chiplets. Anyone who's worked in cryptographic computing before knows that these things need a lot of on-chip memory, a lot of SRAM, potentially a lot of DRAM bandwidth. So we're also planning to standardize a SRAM chiplet. We'll have dual port, we'll have single port, and have all that you might need. We'll also include a template for a Cryptolet chiplet. So say you want an NTT chiplet or something like that. You can use the template chiplet, plug in your kernel accelerator or multiple kernels within the same chiplet, whatever you want, but that'll be good to go. Again, lowering the barrier to entry for folks who want to get involved. Finally, our last pillar is all about evaluation and trustworthiness. So the first thing that we're going to do is create standardized benchmarking. So of course, we're going to have machine learning. Everyone wants private machine learning. We're going to have support for that. But we're also going to look into other things. So I think genomics is a big one we're seeing a lot of folks talk about today. So we're going to have genomics workload. Tushar's an expert in that. He's going to be porting his stuff into Cryptolets. So you can all benchmark your chips using genomic workloads. And anyone in the ZKP space has probably heard a lot about blockchain, or everyone on the call has probably heard a lot about blockchain. So we're looking into financial benchmarking as well. So yes, we're going to have machine learning, of course, but we're also going to go beyond that and include genomics and financial style workloads. And then on the formal verification side and trustworthiness, Caroline's been working to extend her RTL2 micropath paper and work on formal verification. It was published a couple years ago in Micro, and to actually verifying the Cryptolets IP. So you'll be able to verify correctness and eventually test for side channels. The whole idea is that we want everything fully automated. So an automated verification, automated validation, and full reproducibility. So even if you don't want to use Cryptolets, but you want to benchmark against, say, a previous accelerator, it should be really, really, really easy to do that. And that's what we're building towards. Another exciting thing that we're really eager to get going this year is the Cryptolets design competition. So what's kind of unique about this project is that we have allocated about $100,000 a year for prototypes. And this isn't money for me and the team. This is actually money for the community and to build up the community. So what we're going to do is we're going to host a design competition, which is going to be announced very soon. And then anyone will be able to participate in the competition. You can upload your design. And if you have a really high performing design, it'll be evaluated by a team of experts. There's an opportunity for you to get space on a shuttle run that we'll be hosting through the Cryptolets program for fabrication. So what this means is that even though you're not part of that core, Cert Grand team, you have access to this funding to actually tape out a chip with us effectively for free. So we hope this is exciting. We hope to see a lot of really competitive Cryptolets designs come in that we'll have to review. And then we'll take the top ones, integrate them into an SoC, and we'll all tape out a chip together. So stay tuned. We're going to be announcing updates shortly, and we're super excited about that. Also, again, this is all about building community, right? And we've already started our community building efforts. So if you were at Micro 2025, we held the first instantiation of ZK Arch, zero knowledge proof architecture. That was in Korea. And in case you're going to ISCA, or if you'd like to go to ISCA 2026, late June, early July, down in Raleigh, we'll also be having a full half-day tutorial just on Cryptolets. So that you can see here, this is all the Cryptolets team will all be there in person presenting our ideas. So if you're interested, please show up to the tutorial. That one's a tutorial. We'd love to see you, chat with you, and we can tell you way more about the project. Okay, so that's going to conclude the Cryptolets overview. Now what I'm going to do is transition into actually a technical talk, and I'm going to get into some of the work that we've already done in Cryptolets. And what I'm going to do is actually focus on zero knowledge proofs, ZKPs, or zero knowledge proving. So we're just gonna jump right in. So typically in this is a very high level overview because I don't want to give a whole talk on zero knowledge proofs. But within ZKPs, typically what happens is I have some program that I want to run some proof on, right? Excuse me. So I represent that program as a bunch of polynomials. And then once I have polynomials, these are really powerful data structures. Within ZKPs, I typically have two things that I want to do. I want to check for correctness, and I want to do commitment to my actual data. So my correctness checks, that's what gives me my actual integrity. So right, think back to the original example. Alice said she's over 17. The correctness check is what's actually going to give that guarantee, that integrity, that proof that Alice is in fact over 17. Typically, we're going to use sum check for that. Now, there's a bunch of different ways to do it, but typically we use sum check. The other aspect of ZKPs, remember, that's the proving part, is the zero knowledge part, the confidentiality part. That's where we use commitments, and typically for commitments, we're going to use MSM. There's other ways to do it, but for now, for this talk, we're going to use MSM, and I'll explain all about MSM in a minute. And to start with Cryptolets, we're really going to hone in on this MSM. And the reason for starting with MSM is if you look at a time breakdown of a popular ZKP, this is from Hyperplonk from our ZK speed paper, MSMs actually dominate runtime, right? So you can see SumCheck and MSM obviously dominate the majority at 93% of the total ZKP proving runtime. But within that, even MSMs take up 77%. So we're going to start with MSM. So what is MSM? MSM stands for multi-scalar multiplication. And really, at a high level, all it is a dot product on an elliptic curve. So we have our W, which is called a witness. That's from our polynomials. So we took our program, we translated it into polynomials. That's W. It's just basically a bunch of really wide word scalars. You can think of having a lot of them, and each of them being about 256 bits. So we're going to multiply that by P, where P are our points on the elliptic curve, and that is from our proving key. So they're typically tuples. So you have 3D points, and these are very large. So each of these is 381 bits. There's other parameterizations that look slightly different, but you can think of having 256 bits and 381 bits as a good mental model of the sorts of computations that have to happen here. So we want to do a dot product between these two data structures. Okay, well, expensive, but not that bad. Well, the first problem is that you want to do dot products, so you want to do point multiplication, but you don't actually get multiplication on the elliptic curve. So you can't do it. So you basically have to do point multiplications as a bunch of point additions. So of course, what you do is you say, okay, I want to multiply 3 by P1. So I have to add P1 plus P1 plus P1. 5 times P2 is actually P2 times P2 times P2 times P2 plus P2, and you get it. So not ideal. We would prefer to have multiplication, but maybe not a roadblocker just yet. So what's the problem? Well, the problem is that point addition and MSMs, naively, are extremely expensive. So if we want to do a single MSM, we're talking about maybe 2 to the 20 point multiplies. 2 to the 20 for a ZKP, it's actually not even that big. So that's the number of scalars that you have, each of the scalars being 256 bits. We'll go up to like 2 to the 30. So this is actually in some sense a conservative number, but it's fine for now. And then for every point multiply, remember, each of those scalars is 256 bits. So you have to add those points that many times. So you potentially have to do 2 to the 256 point adds per point multiply. Now break that down even further. Point addition is really expensive. So every single point addition is actually 16 modular multiplies. And if anyone's done modular multiplication before, you'll know that typically you have about 3 multiplications per modular multiplication. So to naively do 1 MSM, you have about 2 raised to the 280 modular multiplies. And if you want, you can multiply that by 3. That's how many actual multiplications you have. That's not feasible. Very fortunately for us, we have Pippinger's algorithm. So what Pippinger's algorithm does is it's a huge optimization on this naive approach to make MSM computationally feasible. What it does is it takes the scalars that you have, that's that W, and it chops it up into parallel windows. So each of these red boxes you can think of as a window. So we're just slicing the bits of all of our scalars into windows, and we're going to process one window at a time. Then what we're going to do is we're going to look at this chunk of an individual scalar within a window, and we're going to treat that as an index to a bucket. So we're going to use this to index a bucket for each corresponding point, and then we're going to accumulate each point in that bucket, and then do point additions within that bucket. So all we have to do for each window is number of point additions, and then at the end, all we have to do is multiply by this scalar. So let's take a slightly different look at this visually to understand what's going on. This is the same window scalars here. We've just windowized them. So we have 3 bits per window, and we're going to use each of these 3 bits per scalar to bucket the corresponding point. So these are indices or pointers into buckets. So you can see P1, that is, what is that, 6. So that's going to, P1 is going to go into bucket 6. P2, also 6, going to go into bucket 6. P3, 3, goes into bucket 3. P4, 1, goes into bucket 4. Once we have each of our points bucketed, we can do our point additions. That's going to give us the total accumulation of points per bucket. And then all we have to do is this much simpler, basically constant addition by the value of each bucket. So you can see this is 1. So P4, I just have to multiply 1 by B1. And I had P6. When I had P1 and P2, that goes into B6. And I multiply 6 by B6 to get the result. And then I sum all of these together. So this significantly reduces the number of p-adds that we have to do, because the number of p-adds no longer depends on the total magnitude of all the scalars like we did in the naive method. Now, where are we going with this? Well, you can see here, right? Each of these sums, that's not actually just an adder, right? Those are actually point adders because these are points. So each of these is really big. Those point adders, remember, are 16 modular multiplies. So maybe we don't want to allocate 1 per every bucket. Maybe we want to try and share them. But the second problem is that even if we could allocate 1 point, we didn't care about area, right? We just allocate 1 point adder per bucket. That may also just be extremely wasteful, because what happens is that I'm accumulating partials, right? So I have my B6 partial here in this bucket. I have to add it to P2. Well, this point adder is actually a really deep pipeline. Think dozens to hundreds of pipeline stages just for the point adder data path. So as soon as I put B6 plus P2 to do my partial in here, I can't throw P1 down that pipe because I have to wait for that partial to finish. So my utilization of this point adder is terrible. And so what that means is what I want to do is I want to share the point adder pipeline, which is really deep, across accumulating buckets. But I want to make sure that my pipeline's not so deep that I don't still have one of those buckets accumulating in the pipeline by the time I come back around to it. So optimizing the point adder both for area, because obviously I want to optimize area, I want my chip to be efficient, and for pipeline depth, really has a significant effect on the efficiency of Pippinger's algorithm and MSM, which, remember, that is 77% of your ZKP, so of your overall efficiency of the ZKP. So to address this question of optimizing point addition, We developed the Locus framework. So this is a fully automated optimizing point adder hardware framework. And it's really come to serve as the foundation of Cryptolets. So this is how it all comes together. Much of this code is already checked into the Cryptolets repo. It's publicly available. You can check it out. And what Locus lets you do is optimize any curve. So there's not just one elliptic curve that you can do MSMs over. There's a bunch of them. In fact, there's two major types. There's short Weierstrass and twisted Edwards. We naturally support those right now. You can go check them out. We also have it parameterized. So if you want to tweak the coefficients or the primes, you can do that, no problem. We all typically tend to stick to the sort of tried and true or tried and tested named curves. So if you've read ZKP papers, you might have heard of like BLS 12, 381 or BN 254. These are really popular ones in ZKP. Those are just natively supported in there. They're really easy to run, but we didn't keep this just as ZKPs. We also support typical curves for cryptocurrency and Bitcoins and things like Twisted Edwards for digital signatures. So it's all in there. This is a high-level synthesis framework. So if you go, you'll see the source code, and we're pushing the EDA scripts now for you to run this all yourself. So you can go in and check that out. And we're also pushing all the tests. So if you want to develop your own optimization or anything like that, you can just test it against our validation scripts to make sure you're still passing. We're also working to push hard designs. So if you don't want anything you just say, hey, you guys have a great point adder. I just want your RTL. We're going to push that RTL too. So you don't have to run the HLS flow. You can just grab the RTL directly and use it in your design. So you might say, okay, well, why do you have an optimization just for point addition, an optimization framework just for point addition? It sounds a little excessive. This is a data dependence graph of short Weierstrass. This is a BLS 12381. It's going to look very similar for BN 254 too. Again, very popular curves that a lot of ZKPs use. This is a level dependence graph. So as you can see, there's a lot going on. This is a single point addition. A couple points to make. There's 16 modular multiplies and about 20 modular adds in this graph. So there's a lot of computation happening. This is also a fairly deep circuit, right? There's 5 levels to this. So that's where this really deep pipeline comes in that I was talking about in the Pippinger's algorithm example. And again, I know these say add and mul here, but these aren't just additions and multiplications. These are actually modular additions and modular adds. So things get really complex. These aren't single cycle ops. These are going to have to probably get split across multiple ops. So you want to be really careful how you implement and optimize these things, because if you do it wrong, if you have, say, a poor modular multiplier, the cost of that poor design is going to get multiplied through all the different times you use it in this individual point add. And I also want to drive this home, right? When we say BLS 12381 or BN 254, these do tend to be the bit widths of these optimizations. So we're not talking about, sometimes in machine learning, we talk about 4 bits, 8 bits, 16 bits. Crypto is very different. These are very large bit widths. So we really need to be careful how we implement these things in hardware, or the costs can get extremely high. So what does Locus let you do? Well, first, it lets you pick the operational, we call it operational word width. You can think of it as the base word width. That's the lowest level hardware parameter that's actually going to get implemented as hardware. So eventually you're going to have a hard fixed multiplier implemented in RTL. That's going to be the base word width. Typically, we use around 32 or 64, but this is fully parameterized, so it's up to you. And at that level, that hardware is going to be generated by the tool. So either high-level synthesis directly by itself or something like Designware. For all of these designs, you have an option of having a fixed prime or a variable prime. So if you know, hey, I only want to do ZKP X, and that uses this prime, you can commit that to hardware, propagate those constants into the multipliers, and let it optimize, let design compiler optimize the full data path and get those extra wins. Or you can keep the primes variable, and we'll support some max field size, like 64-bit or 128-bit. You won't quite get the same efficiency as the fixed prime because you can't propagate those constants, but you get much more flexibility and programmability. And then one of the things we found was really important to do is actually choose your decomposition. So we have, remember, 381-bit operations here. We're not going to just say, okay, I want a 381-bit multiplier. It's going to grow either by 3x with bit width or quadratically with bit width, depending on how you do it. We need to decompose that 381-bit multiplier into much smaller ones, eventually down to the operational or base word width. And there's a couple different ways to do it. You can do it with Karatsuba, which is shown here. Many of you may have heard of this before, or you can do it the naive schoolbook way. So if you just read, the textbook on Karatsuba and schoolbook decomposition, you would say, okay, well, I'm always going to do Karatsuba because Karatsuba trades additional additions and multiplications to save a multiply. And remember, modular multiplies are very expensive. We typically want to avoid them for area efficiency. But if you look at this a little longer, you can say, okay, well, yeah, in Karatsuba, I do save, there's four multiplies here, there's 3 here. But in Karatsuba, I can see my critical path through this circuit is actually much greater than schoolbook. So there's a trade-off. Do I want less area or do I want a faster critical path? And remember, in Pippingers and in MSM, the depth of that pipeline when I'm doing the bucketing and the reduction actually matters quite a bit. So it's not totally obvious which one is better. Well, in Locus, we support both of them and we support hybrid solutions of both of them. So at each level of decomposition from 254, 381, all the way down to your base word width, you can say, okay, I want to do Karatsuba, I want to do schoolbook, and just do a design space exploration and get the best for me. And that's exactly what we do. And then finally, this is all HLS implemented. So we also do, of course, directive tuning to get super good performance. We'll help you with your pipeline, your latency, your II. And something else we found to be really important when we're experimenting with this is the actual functional unit implementation. So how you do your adder tree, because you're going to have a bunch of these. And if you don't optimize them properly, it's going to come back and bite you. So we implemented this thing and we used it. We used it to do design space exploration of all those different named curves for thousands of points. So what you can see here, all of these faded points, these are non-Pareto optimal solutions. Each of the colors represents a particular curve. You can see that in the legend here. And then the shapes of the points along the Pareto frontier indicate whether we're doing Montgomery reduction or Barrett reduction. So a couple takeaways. First, you can see, well, yeah, Locus was actually super important because there's a lot of really poor performing designs far away from the Pareto frontier. So if you didn't explore this design space, you run the risk of losing a lot of area and a lot of performance. You're leaving a lot of money on the table, a lot of chip area on the table. So you should be doing design space exploration for your PADs. The second thing, which was actually pretty surprising to us, was that for a lot of the curves, you find trends like you'd expect. Okay, Montgomery tends to be more efficient than Barrett. So if you only care about Pareto optimal, which I suspect most of us do, you would do Montgomery reduction. But for a couple of the curves, especially as you get into the twisted Edwards down here, the Montgomery and Barrett actually both lie on the Pareto. So that means that the Barrett was actually better than the Montgomery in certain situations. That was a little surprising. We'd never seen that before until we really dug into the results of our design space exploration. And it wasn't a bug. What we found is that for these two curves, the twisted Edwards and the digital signature ones in particular, the Barrett modular multiplication constant mu is much more simple than Montgomery's Q prime. So this is for if you have a fixed prime, a constant, you're trying to propagate those values into the actual multipliers to optimize the data path. If you look at the Q prime here and the mu here, the Q prime is used for Montgomery multiplication, the mu is used for the Barrett. So you can see the Barrett's constant mu, it's actually trivial. So when it propagates that constant into the actual multiplier data path, it's really able to optimize it really well. But the Q prime, not so much, right? This is really complicated. And what it's trying to do is it's trying to reduce the strength of the multiply into a bunch of shifts. So it still is a pretty complicated circuit compared to the mu, to the point that we can actually see Barrett is on the Pareto frontier. So nice little insight takeaway from the design space exploration, something we were not expecting, and really a motivator for doing design space exploration for point adder design. All of this is now publicly available through Cryptolets, so you're free to use it in your work. If we compare the locus point adds to prior work, we do really, really well. So what we did is we took point add design philosophy from SZKP and ZK Speed. This is recent work from our group published in PAC and ISCA. We used the exact same approach. We ran it through the exact same tech node, GF12, exact same frequency, 1 gigahertz, tried to make everything the same. And let's just look at this BLS 12381 because that's a really popular curve. That's what's used in Hyperplonk. You can use it for Groth 16 as well. So in prior work, the latency was 82 nanoseconds, and the area for a single PAD was about 12 millimeters squared. So this thing was huge. And remember, we're running at a 1 gigahertz clock. So 1 nanosecond, that basically means you had an 82 stage pipeline just to do point addition. This thing was massive. So for Locus, we did both the fastest and the smallest. But if we just look at the fastest here, we're able to reduce that pipeline down to only 31 stages. That's a 2.65x speed up in terms of pipeline latency, which is great because it opens up a whole bunch of different optimizations we can do at the Pippinger MSM level. But we're also able to reduce the area. So we're able to be much faster and much more area efficient because Locus just does much better job with the decomposition and that exhaustive design space search, tuning all the different parameters. So that's great, but what if we plug it into a full MSM accelerator? Because at the end of the day, right, that's all we really care about is how much faster can we make MSM go? Because that tells me how much faster I can make my ZKP go. So what we did is we took our point add Pareto designs from the previous study, that last design space plot I showed, and we plugged it into an MSM design space exploration study, again, to compare against prior work. So what we did here is we didn't actually change the architecture or MSM accelerator design. So you can go look at SZKP or ZK Speed to see how we accelerated it, or maybe I'll cover it in a different talk. So that stays the same. All we did is we changed how the PAD was implemented, whether or not it uses the standard one from the previous slide or the optimized locus one from our design space exploration. We plugged it in and we did a sweep over parameterizations of that MSM accelerator. So we considered a bunch of different scalar widths. I'm only showing the BLS 12381 here. We varied the PE count, so you can have a bunch of different MSM, basically how many cores you have for your MSM unit, the window size, how you chunk your scalar, and how large your on-chip area is on chip. So those are the things we did. We swept thousands of designs for area and latency, plotted the Pareto frontiers, and this is some results for BLS 12381. You can see the baseline design is in red here, locus is in blue, and we consistently get substantial performance benefits using locus just by optimizing the point add alone. So basically what's happening is because we're able to reduce that massive area cost of the point add, we're able to allocate more point adders, more PE cores in the same amount of area within this 50 millimeter squared limit that we're showing here. And we're able to use that little bit of extra space we have to increase the on-chip area. So ISO area, we're able to get about 2.4x speed up, right? So we can have more function units and more on-chip area. We're just not wasting the space on inefficient point adders. And we consistently see this across different curves. We're getting about 3x less MSM area in GF12. So we're pretty excited about that. And with that, that was Locus. As I said, so Gurav here, he's done a ton of the work on making all this happen in collaboration with Alhad, two of the students working with me here at NYU. All of the code is right now publicly available in the Cryptolets repository on GitHub. So go check it out. Let us know if you have any questions. And thank you all for calling in, and I'll stick around to answer any questions folks have. So thank you.